Okay, hello everybody. We are looking here at the higher questions on topic P6, looking at particle diagrams, changes of states, specific latent heat, that sort of stuff. And so we're starting off with question 1, which is about one of the subjects that I didn't list here, which is all about density. And it's asking us what is the correct equation to work out the density of a material, and we've got 3 particle diagrams above which are showing us A, B and C, 3 states of matter, and that'll link into a later question. So equation for density then is that the density of a material is equal to the mass divided by the volume. That's all there is for our first equation for question 1a. Question 1b then. A student explains density to his teacher using the particle model in the figure above. His teacher says there are limitations to the model. Give 2 limitations to the particle model or of the particle model in the figure above. So there's a few different things that you could say here. We could talk about that we're not showing forces, so there are intermolecular forces between particles and there are no intermolecular forces shown, these forces of attraction that hold particles together in solids, liquids and gases. We could also say something along the lines of that they aren't shown as spheres, it's circles on a page, not spheres. So particles shown as circles, not spheres. And that's enough for our 2 marks there, 1 for each point. We could also say that the particles aren't necessarily all the same size. So the particles in the diagram look to be slightly different sizes in some parts of the diagram compared to the others. So we could say something along those lines as well. And then last part of question 1, 1c, says when the gas in a container with a fixed volume is heated, the pressure increases as the temperature increases. Explain why the pressure increases and use the model, the figure above, the model in the figure above, there we go, to help you. So this is very similar to a 6 marker, but it's a 4 marker instead, okay? There are 4 particular points we need to make, but I would still recommend planning this out somewhat as you would a 6 marker and think about the key things that you need to say, okay? So key thing that happens here is that as I increase the temperature, the pressure increases. I need to show that in 4 points, okay? So what I'm going to say is, in my notes on the side, is I'm just going to write inc temp, so increasing temp, the temperature, increases the kinetic energy of the particles. If the particles have more kinetic energy, that means that so that's linked into this. This is then linked into saying more kinetic energy means they move faster. If the particles then move faster, that means they're going to hit walls more often. Now that might well be enough to get the marks written out like that, but I'm still going to write it out as complete sentences just to make it clear to the examiner what my answer is, okay? So what I would first say is as the temperature increases, the particles gain more kinetic energy. First point. This means, I'll tick off actually what I've done. So more kinetic energy means moving faster, which is what I'm about to write. So this means the particles move faster and hit the walls of the container more often. Now this is going to cause an increase in pressure. Each time those particles hit the container wall, they're going to exert an outwards force on that container. The more times the particles hit the wall, the more forces, or the more times that force is applied to the wall. So that's my last little point here, which I didn't write on my little notes, is increase in force outwards, which is what your pressure, that's what your pressure is. So as the temperature increases, the particles gain more kinetic energy. This means the particles move faster and hit the container walls more often. This then causes a greater outwards force on the container. And there are my 4 points for the mark. I've got for the marks. I've got one there talking about temperature increases, particles gain more kinetic energy. This means they move faster and hit the container walls more often. This then causes a greater force. So where I've put each of these dashes is sort of like each individual point, and that's what I'm getting my marks for. So question 1C, the 4 marker, then swiftly followed up by a 6 marker, all about particle diagrams and arrangements. Okay, so the diagrams here show the arrangements of particles in a solid, a liquid and a gas. Use the diagrams above and your own knowledge to compare solids, liquids and gases in terms of their particles. So I need to be talking about what their particles are doing, and I need to also talk about the arrangement, I need to talk about the movement, and I need to talk about the energy of the particles. Okay, now this is again where planning in advance and thinking about how you're going to lay your answer out is really important. Okay, essentially it doesn't work out exactly this way, but there are 6 marks for the question, and there are 3 things I need to say about the 3 points. So essentially I've got to make 9 points to get my 6 marks. Okay, it doesn't work out exactly 1 point to 1 mark, but as long as I hit these 3 points for the solids, liquids and gas, that would then get me everything that I need. So what I'm going to do is I'm going to lay my answer out like this. I'm going to write solid up here. I'm going to write liquid in the middle. And I'm going to write gas down here at the bottom. And what I'm going to do is I'm going to try and talk about arrangement of solid, liquid and gas, movement of solid, liquid and gas, and the energy of the particles in a solid, liquid and gas. And it's almost like a 3x3 grid of where I'm going to write my answers. And what that does is it makes sure that I don't miss out on any of the points that are going to get me marks here. Okay, just by that little bit of planning there and highlighting the key bits of information. So arrangement comes first. Look at my particle diagram. Arrangement of a solid, a liquid and a gas. Okay, so solid particles are arranged regularly, which means that they form into these sorts of patterns of columns or rows of some kind. So the solids are arranged in a regular pattern. Liquids and gases, on the other hand, are irregular and random. Okay, so I'm going to say the liquids particles are arranged irregularly, and the gas particles are also arranged irregularly, but they're more at random. They can spread out and be anywhere in the container, whereas the liquid particles have to be touching each other. So I'm going to say for the gas, they are arranged randomly. So that's arrangement done for a solid, liquid and gas. Now let's talk about movement for a solid, liquid and gas. Solid particles, they vibrate on the spot. They do not move around at all. They just vibrate on that spot and can't go anywhere. You might say about fixed points. Okay, they vibrate about fixed points is another thing you can say. In a liquid, the particles move around, but they have to be touching one another. Okay, so move around whilst touching each other, have to be in contact with each other. And then gas particles, they can move around freely. Okay, gas particles do not care about other gas particles, and they move around completely freely wherever they please. Okay, so there's movement talked about. Lastly, last little thing I need to then say is about the energy of the particles. Now, this is one of the harder things to try and understand, but it's all to do with how much they're moving. If you think about it, movement is linked to kinetic energy. Okay, as I've said before, the faster particles go, the more they move, the more kinetic energy they have. So particles in a gas which whiz around all over the place, they've got to have the most energy. Liquid particles which can move around but still have to be in contact with each other, they're going to have a middling amount of energy. And then solid particles, which can't really move around at all, they have the least amount of energy. Okay, so I'll say solid particles, so arrange regular, vibrate on the spot, least energy. For the gas, I'm going to skip the liquid for a second and just say gas have the most energy. And then for the liquids, I could say they have medium energy, middle energy. I'd rather compare it to the solids or gas. So I'm going to say more energy than solid, less energy than gas. And laying my answers out in this little grid has just made sure that I've talked about a solid, a liquid and a gas. I've talked about their arrangement, I've talked about their movement, and I've talked about their energy, and hit absolutely every point I need to get full marks on this. Did not take me very long, it did not take much planning. I can look at my timer and see that I've only been going for 5 minutes and 20 seconds. And that's along with explaining and talking and pausing as I've gone. Okay, so if you guys were doing this for yourselves, you'd hopefully be able to do something like this a bit quicker. So planning it out is definitely well worth it. Okay, so moving on to question 3 then. 3 says the particle model can be used to explain the properties of gases. Describe the direction of motion of the particles in a gas. Luckily, we've already answered this with our previous question. They move around freely. That is at random as well. Okay, so maybe that's something I probably should have added up to here as well. Move around freely. Just going back to question 2, I can also add and randomly. And that random motion is the motion of those gas particles all over the place with no particular pattern. So randomly is my answer for question 3. Flipping over then to have a look at question 3. Sorry guys, looks like my camera cut out there. Question 3b says explain why heating a gas increases the average speed of the gas particles. And this is very similar to a previous question that we've already answered. We essentially are saying that heating is going to increase the temperature of the gas. Temperature is then massively linked to kinetic energy. Okay, so I wouldn't write that down necessarily, but I would say that temperature is linked to kinetic energy. You can sometimes you might want to use the word proportional. So what that means is if I increase the temperature, the kinetic energy goes up. If I decrease the temperature, the kinetic energy goes down. And so if Ke increases, that means that the speed increases. Moving on then to question 3c, says water can exist as either a liquid or gas at 100 degrees Celsius. Explain why a mass of gaseous water at 100 degrees Celsius contains more energy than an equal mass of liquid water at 100 degrees Celsius. So we need to talk about here what we've talked about in that previous 6 marker, about how that how the gas has more energy than the liquid water because of how the particles are moving. And we could also talk about how the energy has been put into it to change the state, that latent heat. Okay, so linking to latent heat here as well. So what I might say is gas particles move faster than liquid particles, so have more energy. And then I can also say energy is also needed to change the state of liquid water to gaseous water. And what that energy is doing is it's overcoming the energy. You could say it breaks or sort of overcomes the intermolecular forces. I don't like using the phrasing of breaking bonds because bonds are more what we talk about in a chemistry sense, whereas when we're talking about between particles in liquid water, it's more to do with intermolecular forces. So the energy overcomes the forces between the particles. Righto, moving on to question 3D then. Water vapour is a gas. Gases change state when they cool. The figure below shows condensation on a cold bathroom mirror. And we've got a volume of 2.5 times 10 to the minus 5 meters cubed of condensation forms on the mirror. I'm told that the density of the water is 1000 kilograms per meter cubed, and the specific latent heat of vaporization of the water is 2.26 times 10 to the 6 joules per kilogram. And what it asks me to do up here is calculate the energy released when the condensation forms. Now, the equation that we need to use to find the energy is mass times latent heat. Okay, mass times specific latent heat. So if I write that in as the acronym as well for you, SLH. Now, I've got the SLH, which is 2.26 times 10 to the 6, but I don't have the mass. But I can find the mass because what it does is it gives me the volume and the density. And I can use that along with my density equation, which I wrote down for question 1. Density equals mass divided by volume. I've got the volume and I've got the density. If I rearrange this equation, I'd have density times volume equals mass. So the first thing I'm going to do is take the density and the volume, multiply them together and find the mass. So that's going to be 2.5 times 10 to the minus 5 multiplied by 1000. So I'll get my calculator, drop here so you can see. 2.5 times 10 to the minus 5 multiplied by 1000, and that's going to give me an answer of 0.025. That is my mass in kilograms. I can then go ahead and chuck this into my specific latent heat equation. 0.025 multiplied by the latent heat of vaporization, which is 2.26 times 10 to the minus 6. Oh, sorry, to the 6, so the positive 6. 2.26. Let's see here. 2.26 times 10 to the power of 6. And that gives me an answer of 56,500 joules. So 56,500 joules. And I'll write that in on my answer line. 50, helps if I write the correct number though. 56,000, let me just write that again. 56,500 joules. There's my final answer there. 56,500. Okay, Okay, so moving on to our final question, question 3E. It says, central heating boilers burn gas and use the energy released to heat water. Modern central heating boilers take advantage of the energy that is released when water condenses. Wastewater vapour produced when the water is heated in the boiler is used to preheat the cold water entering the boiler. Give some of the arguments in favour of condensing boilers compared to older non-condensing boilers. So what we need to talk about here is I need to talk about why these condensing boilers are going to be better than the older boilers. So in favour of condensing boilers. So let's talk about why these condensing boilers are going to be better. Okay, so what I need to be thinking about to answer this question is thinking about energy transfers and what I want from energy transfers in my boiler. Okay, I want my boiler to heat up my water as efficiently as possible. I want as much energy as possible to go into my water and as little as possible to escape or to be wasted. Okay, and when I boil some water, that might then be wasting some energy. So what I'm trying to do is I'm trying to recapture some of that energy. Okay. Now if we think about our equation for specific heat capacity, which is energy is equal to mass times the specific heat capacity times the change in temperature. If I have a bigger change in temperature, I'm going to need more energy to heat my water. If that water comes in and is preheated, where does it say preheated? Here we go. So if that water has been preheated, that means that this is going to be smaller, which means I'm going to need to use less energy to get my water hot. Okay? So because the water is preheated, the temperature change is smaller. I'm just going to write temp here so I can fit it all on. The temp change is smaller. And then linking that into my equation up here for specific heat capacity, this means less energy is needed to heat the water. If I need less energy to heat the water, that means it's going to be more efficient. Okay, so condensing boilers are more efficient, which is a good thing for them. We want things to be more efficient. That means less energy is wasted. Now this is a 6 marker, so I've done a little, similar to a 6 marker. It's only a 4 marker, but I've done a little bit of planning of this in advance, thinking about what I'm going to say. And what I've done is I've made 4 points. So I've got my 4 marks, but I could also go on to talk about why that's good. So as an extra bit, I could go on to say something along the lines of less gas is burnt, so less gas is burnt, and that means less CO2 is produced, which is better for the environment, etc. Okay, so a couple of extra points there on the end. I don't necessarily need to make these points because I've already made these points here, but some of you might have made earlier points and said if it's using less gas, it's producing less CO2. And you might have missed out some points in the middle or some points at the start, but talked about how because it's using less fuel, it's better for the environment.